good afternoon. I'm Liying from Center for Spatial Information Science and the System at George Mason University in the US. So I'm going to talk about automated high resolution LCZ mapping from multi-stream sensing data. So this LCZ, I think in the room everyone know LCZ. It's become a standard for urban characterized urban landscape and it's widely used in urban study. And LCZ have a 17 class, and I think the first 10 or 12 classes about urban landscape structure. So the currently, LCZ classification, we have basically we have a LCZ classification schema, and the classification schema currently is very qualitative. Basically, for example, the class 1 is called high-rising compact class. So there are no detailed definition what means high-rising, what means compact. And the product currently we have a global 100-meter resolution. It's available globally, and this data set are generated by basically the classic method used. Citizen scientist like every city, you have a volunteer or scientist go to the satellite image and draw the area of a class. Each class use this as a training data set to train the machine learning algorithm, and then after the algorithm is trained, then apply back to the satellite image and get a classification. The problem for this method is basically, is very subjective because everyone have every, their idea of which is a high rising area, which is like a low rising and area. And so the result, you ask this person to draw the ground truth and the training algorithm, and then cannot be repeated because next person, draw differently, and so the training data set are totally subjective. And so the global 100-meter data is generated in this method and it's available. But if you examine the data set, you will find that they have many different locations. They have incorrectly classified. And this is just I mentioned this as a problem because the current available. So this study, we try to automate the LCZ mapping, and we want to produce the map that is objectively and it can be reproduced. So if you run the algorithm once again, you will get exactly same result. So what we try to take, because the LCZ class is basically defined based on 3D structure for urban landscape. And currently, the global 100-meter resolution LCZ map is based on satellite images. This satellite image, that optical satellite basically give you 2D horizontal structure, but they don't have the accurate vertical structure information. So this is why we need to do the training for every city. Training data set for every city are different. And in this study, we actually take advantage of a recently available data set called Global Ecosystem Dynamic Invested GEDI data set. This is a larger data set at a 25 meter spatial resolution, and this is point measure. So 25 give you a profile of a 3D structure of this 25 meter resolution. The data set is not continue covers it. Along track is 60 meter apart, but the cross track is 600 meter apart. So you get a mesh of a global cover of 25 meter profile. So we take advantage of this to try to do the automated LCZ mapping. So the objective is that we want to, first of all, we want to establish a decision rules that will automatically generate training samples. So we use the GEDI data set combined with the other satellite data to develop, develop a training data set, and use this training data set to train the algorithm and apply that to satellite imaging. So basically, the study, once we have can automatically generate the training data set, then we can automate the GEDI data productions. And in this study, we select 6 cities across the global. Some are in northern hemisphere, some in southern hemisphere, and in the different climate zone. We want to test our method. We use the same law, and whether or not we can apply to all the different cities to get a same result. This is the data set that we use, the GEDI level 2A relative height point data set. Basically, the data set is available from NASA. And then we also use the Centennial 1, Centennial 2, and the nighttime light image, and also land use laboratory images data set. So this data. And this is some example of the GEDI profile of LCZ class. For example, you have a first class compact high rising, and we select this footprint of GEDI, and you can see that this is the energy return from the GEDI shows the energy return. This is basically point cloud data, and you see that this is the percentage of relative height is like about 100 meter, you get like 100% energy return. So you get the entire profile. This is brown, and then you see this energy return, and this basically top of the building. Okay, so this is another example of compact middle rising, and you can see the return heights and low. This is basically a footprint of. So you can get exactly the third dimension structure of this pixel. So this is another example. So, and based on that, we develop a rule on the relative height is 100% return is larger than 30 meters, and 50% energy return is higher than 20 meters, and then open proportion is 75. We define this rule as a high rising, and that is another rule 2. We define the rules, and 3, 4, 5, 6. These are all open class. So, and we apply, as I said, we apply these rules to the GEDI data set and get the training data set, training the random forest algorithm. And so for each city, we can automatically generate a training data set and training the algorithm, and then apply that to the satellite image. And this is the example of for the Washington, D.C. This is the UDA product, and this is our product. You can see that it's very similar, but we have a more detail. And like this area is high density, but in this map, this area is not high density. But if you go to brown, DC area, we are very familiar. We are, the city, so we know that our map is much more accurate than this without. And this same rule we apply to the Phoenix, and this is our result, and this is the UDA result, and you can see there's significant class difference. And this is Hong Kong area. We use the same rule, and in our case, we generate this map automatically, and this is wood up, and you see more accurate and more detail, and we are general pattern is similar, but we have more detail and more accurate. And this is a detailed example in Phoenix example. This area high resolution imaging. In UDAP, you can see just one class, and we have multiple class high density. And so this is the and also with the GEDR data set that we can actually generate in the area other urban parameters like the building height, standard deviation, other things. You also can generate. So basically, some conclusion, combined with a space LiDAR and the optical data set, we can ultimately generate a high resolution global LCZ, and this product, supposed to be objective and also can be repeated because doing scientific research, real product reproducibility is very important. But the current LCZ product you cannot reproduce. So this is a thing, and there's a next step for us. Once we're going to generate the global coverage at like a 30 meters spatial resolution. So any question?
Thank you. Any questions for Professor Lee?
I think I was right. Can you tell me when might we expect a global map of LCZ using this field?
Probably going to early next year.
Okay.
Yeah, we have a test algorithm and validate it, and we're going to apply it globally. And we will make this available.
Well, give me about the information. Do you actually need local climate zones at all? Because now you actually have a complete description of the morphology of the landscape.
Yeah, yes. This so it depends on application because some application is they depend on LCZ as an input, but it's better actually directly use the information and feed into the model. So we think about instead of currently the over modeling community they use the LCZ and the parameterize and input into the model. This you have a 2 times get possible error because first of all the data to the LCD and then you parameterize that. So, but we think about the directly input. But as I said, that some application they already depend on LCD, so they still have some usage. So.
Thank you very much.